It's children.
Okay. So it's going to be a relatively short lecture. I just want to talk about what a memory register is. And you need to know what a memory register is and how to model one for Lab 5. Okay, because I think I mentioned last week that Lab 5 is basically Lab 4 with memory. Okay, so once you have your Lab 4 working, Lab 5 is just adding memory to it. I want to remind everyone again that Lab 4, that's due this Friday. Okay, so now that the midterm is over, if you haven't finished Lab 4, that should be your priority for this class. And then, like I said, once you know what a memory register is, you'll be able to do Lab 5, but Lab 5 won't be due until Friday of next week. Okay, so you'll have plenty of time to do Lab 5. Thursday's lecture is going to be an introduction to finite state machine, getting FFM. And you won't need the finite state machine for a lab until Lab 6, okay, which will be due November 17th, another Friday. So from here on out, the labs are due on Friday. And that will also be true for the final project. Okay, after Thanksgiving break, when you come back, the final project is broken up into two parts, an individual and a team. The individual is due Friday the 9th week, and the team is due the last Friday the 4th. So from here on out, there's labs due on Fridays, and I'll talk more about the final project when we get closer. Okay, but just to give you some orientation as far as what's left of the labs. Okay, so first thing is from last time. This is just a repeat of the Verilog code, the system Verilog code to model a D flip-flop. So if you didn't take a picture of this last time, I would take a picture of it before you go today, because this is how you model the flip-flop, the D flip-flop that's needed in Lab 5. Okay, so I'm giving you the code. The only thing that I really didn't give you is how to declare the inputs and outputs. But by now, that should be, cookbook, right? But remember that since Q is an output defined within an always block and always FF, you do have to use logic, right? You got to put outputs, logic, and Q. Okay, but anytime you have an output within an always block, whether it's a cone or whether it's an FF, you have to put that logic for the declaration of the output. Okay, and again, key thing here is that when you have an if statement, if you leave out the else, that's what creates a latch, or at least that's one way to create a latch. And that's what we want to do here, right? Because with this flip-flop, if we're not resetting it, and remember, reset means that it'll make Q equal to 0. And if we're not setting it, and remember, set means making Q equal to 1. And if we're not loading it or entering it or enabling it, again, enter, enable, loading all mean the same thing, where you're assigning Q to whatever's on the D input. Well, if you're not doing any of those things, you want your output just to stay the same. You want the next state of your output just to be equal to the current state, right? But you want to retain that data. So this is when storage is happening, okay? So here you're intentionally leaving out the else because you do want storage, okay? All right, so any questions on a D flip-flop? Again, this is, we covered this last week. That was one of the last things we did, I think, is, this code here. Has anyone had a chance to try this yet? Okay, didn't think so. Right. Just curious. All right, well, new stuff now. Okay, new stuff for this lecture is a memory register. Well, a memory register is just a device that can store multiple bits. So it's made out of multiple D flip-flops, where each D flip-flop is storing a bit. So this is similar to the adding circuits we talked about, right? That, we had like our full adder and our half adder, and like your single adding circuit can only add a single bit. So if you want something that will add multiple bits, right, you need multiple adders, right? You need an adder per bit column that you're adding. Well, similar to that, when you're storing bits, you need a flip-flop per bit. Okay, so if you're just storing a single bit, a D flip-flop is fine. But if you're storing multiple bits, you now need a register, okay, that's made out of D flip-flop. So in Lab 5, you're going to have a 4-bit memory register, and it's made out of 4 D flip-flops. You know, in CP233, the microprocessor that you build in that class has 32-bit memory. You know, so each register, each memory register in that microprocessor can store 32 bits. So there's 32 flip-flops in each one of those registers. And you have like lots of registers too. So you can just imagine how many flip-flops there are. So if excuse me, if you look at how the D flip-flops are connected in a memory register, well, you'll see that they're basically in a parallel fashion. All the D inputs are connected together. So, you know, here we have a 4-bit D input instead of just a single bit like a individual flip-flop has. And this flip-flop will be storing D0, D1. You know, we could write that in here. This would be like D0. This would be like D1, D2, D3. Okay, so all the D inputs go to a 4-bit input, and they split up. Okay, just like remember the adding circuit, like the two numbers you were adding, right? You'd have like A that was 4 bits, but then like the 0th bit went to the half adder and so on. So it's very similar, the structure. All your Qs come together, okay, for a 4-bit Q output, kind of like how the sum bits came together for the adder. Now this is different than the adding circuit because the adding circuit was combinational and didn't have a clock. Okay, when you have a sequential circuit like memory that has a clock input, most often you'll see those clock inputs all connected together and they all go to the same clock signal. And that's what puts these all in sync. Okay, they're all following the same clock signal. Okay, so this is what a memory register structure looks like. Now to model this in System Verilog, you could do the same approach that we did with the RCA, right? The ripple carry adder. Because remember the ripple carry adder, after you modified it for Lab 4, you had all half adders, right? And you know, we connected these all up. Remember that? We're not going to do it that way this time. Okay. We're going to let the software do the work. Okay. Because a simple way to model this memory register in System Verilog is to take the same exact code that's modeling the D flip-flop and just doing this. Instead of declaring D as just a single bit input, you're going to declare it as 4 bits. Right? So you can literally copy this code for the D flip-flop and then just make this edit for D. Okay, also do the same thing for Q. Make it 4 bits now instead of a single bit. And the other thing you'll have to do is, since Q is now 4 bits, when it gets reset, you just want to make sure that that's supposed to be, but I'll put it as a comment. You would just replace this with Q assigned to 4, tick mark B, and then 4 zeros. And you do the same thing for set, 4 ones instead of just a single one. See, you could have done that for the RCA. Once you made the RCA just 4 full adders, you could have took the full adder code and just did the same thing, like just relayed the inputs multiple bits and the output. See, we didn't tell you that then because we wanted you to get more practice with the whole structural model. Okay. And truth be told, the ripple carry adder, that adding circuit, it's sort of like an outdated adding circuit, like it's not very efficient. There's much more efficient adding circuits, and in fact, if you were to put into System Verilog, an adding circuit with the 3 to 0, for the inputs and the outputs, like we're doing here for the memory register, System Verilog would actually model not an RCA, they would model a different type of adding circuit that's more efficient. Okay, but anyway, we had to do the the RCA, the not so efficient adding circuit just for academic reasons. Okay, you wouldn't actually use an RCA in practice. Okay, but anyway, the big point here is that once you have this flip-flop module working, and again, I gave you most of it, you just got to declare the inputs and outputs. All you got to do, copy paste this code, make these few changes, and as long as you don't make any mistakes when you do the editing, you should have a working register. Okay, so is there any questions up to this point? Is it clear what you need to edit here to go from the flip-flop to the register? Okay. All right. So, yeah, just to kind of drive this home now, the flip-flop high-level black box diagram, you're going to have a single bit D input, single Q output, and your clock is always single bit. The high level for the memory register, well, you'll have your single bit clock, because your clock is always single bit. Okay, but now you're going to have a 4-bit D input, and you're going to have a 4-bit Q output. Right? That's the only difference between the register and the flip-flop, is the number of bits on your input and your output. Okay. See why this is a good lecture for after an exam, right? You don't have to think too much, right? Okay, let's move the camera. And the rest of what I want to talk about deals with Lab 5. So let's move over here. Let's see. Yeah. All right, so this is where you want to look at the handout that's on the table. There should be enough of these handouts for everyone that's at the table. If not, let me know. I have more copies up here, but there's a handout that's two-sided. There's diagrams on both sides. So this is your Lab 5. So look at this side here. That's got the X's. Okay, so this is your diagram from Lab 4. And for Lab 5, you're going to use just about all of Lab 4, except for what you see X'd out. Okay, so for Lab 5, we're not using this decoder any longer. We're not using the neg output any longer. And we're not using this mux that had the validity bit connected to its select. Okay, everything else you're still going to use. So you're using this part of Lab 4, and then you're going to add this. Okay, and that's what Lab 5 is. So look what you're adding. You're adding 3 registers. Okay, so that's your memory. And you're adding this other module over here that's labeled Universe SA. This module here, the Universal SEG, SA, that's provided, at least the code is. We provide a text, it's a text file. It's not a System Verilog or a Verilog file. It's actually a text file. So you're going to have to copy and paste that text into actually a Verilog source file, because Dr. Mealy wrote the code for this module, and he wrote it in Verilog. Okay, now Vivado, you can run mixed files. So you can have all your files in System Verilog, and Dr. Mealy's is going to be in Verilog, and it will all run together fine. Okay, What Dr. Mealy's module does is that it does time multiplexing. So this will allow us now to put data on each of the 7 segments at the same time. See, without a multiplexer, all the 4 displays would show the same data. Like for example, in your lab 3 and your lab 4, if instead of just, instead of having 1, 1, 1, 0 and just showing your result on the furthest to the right display, if you had all zeros where all the 7 segments lit up, it would just show the same data. Okay. The only way you can get different numbers on the displays at the same time is by doing time multiplexing. Okay. And that has to do with how the 7 segment displays are connected. They're all connected in parallel. Okay. And quickly, what time multiplexing is just that data is being shown on the furthest to the right display. So let's say, like 1, 2, 7, 9 was the result that you want to show on the 4 7 segment displays. But what the time multiplexer does is that it puts the 9 on the furthest to the right display, then it puts the 7 on the next display, and the 2 on the next display, the 1 on the next display, and then it just keeps repeating. And it does it at such a rate that our eyes can't detect that the numbers are changing across the displays. We just see a steady 1, 2, 7, 9. Even though the 9's there, then the 7's there, then the 2's there, then the 1's there, and so on. Okay, so that's what Dr. Mealy's module is doing. And we provide that module because to ask someone to do it that's just learning Verilog and just learning digital logic, it's beyond the scope of what's expected in an introductory class. It's beyond the scope even of a 2nd level class. I mean, it's more like a 3rd or 4th, 4th level type of modeling. Okay. All right, so let's see. You should be able to tell me, looking at these diagrams, okay, both of these diagrams, right, one on each side, you should be able to tell me what the high-level black box diagram for lab 5 is going to look like. Maybe we call this the adder, subtractor, stemming. What would you put on the input side here? What are our main inputs? A, B, sum. Okay, so that's just like lab 4. Yeah, I was gonna ask, anything else?
Yeah, block entering either.
Yeah, this might not be as obvious because see, if you go over to the this diagram here, there's not a dash box, and that's actually my fault. I should have I should have put clock, enter, and clear outside the dash box with the other main inputs. But you see, that's what we're gonna have to add to our high-level black box diagram for lab 5 that lab 4 doesn't have, right? Because lab 4 didn't have memory. So that's why you didn't see a clock, right? Because again, you only have a clock when you have sequential circuit like memory. And then also we have an enter and a clear. Because those are going to hook up to the enter and clears of our flip-flops. Okay, remember, clear is the same thing as reset. Enter is the same thing as enable. Okay, so yeah, we're going to have clock. What does that little triangle thing mean on the clock input? Did you pick that up from last lecture?
It means it's falling edge.
Well, it just means it's edge sensitive.
Oh, edge.
Yeah, there's no little circle that's rising edge. If there was a circle, negative or falling edge. But yeah, that little triangle just means that it's edge sensitive. Because remember, flip-flop, that's what it is. It's an edge sensitive latch. Okay, so yeah, we got the clock, and then enter, enable, same thing, clear. Again, clear and reset are the same. Okay, so these are all single bit. You got the 2 4-bit numbers that we're adding or subtracting. Okay, how about on the output side? What are we going to have?
An 8-bit segment and 4-bit A.
So seg. So AN's 4 bits, just like it was for lab 4. But how many bits was seg in lab 4? 7. Here it's 8. Okay, the reason why it's 8 is because Dr. Mealy's universal seg, that's seg, I always say seg, it's a seg. His module uses the decimal point. Okay, the decimal point is the 8th segment. I don't know if you noticed that in constraints, but in constraints, there's one of the segments that says DP. DP stands for decimal. Okay. All right, so that's what your high-level black box diagram for lab 5 is going to look like. So again, this is useful because it gives you the main inputs and the main outputs. Okay. So the suggested order of lab 5 is first create the D flip-flop and then test it. Okay? And when you test it, you want to make sure that all of this functionality works, right? You want to make sure the reset works. You want to make sure the set, you make sure that int works. You want to make sure the storage is working, right? And it's not doing any of this. It's retaining the previous output. You also want to test priority. And how would you test priority? How would you test like reset having priority over set and enter?
Have them both active.
Yeah, exactly. Just activate all of them, right? They're all active high. So make them all high and make sure it's reset. Right? So that's how you check the priority. Okay, so yeah, just make sure that you can check all possibilities. I mean, you can look here and see how many single bit inputs you have. And I forgot to put a set here. We don't need set. Oh, you don't need set. Oh, I'm going to explain that later. Yeah, even though your flip-flops have the set input, notice that the high-level black box diagram, to add or subtract memory, it doesn't have set, it just has clear. Okay, but I'll point that out coming up why that's set. All right, so once you have your D flip-flop all built and it's testing the way it should, then go ahead and create the memory register, which again, you just got to make a few edits. Okay? And you basically are going to test it the same way. Now you're just looking at more bits on your output. That's basically the only difference. All right, now here's something new that you haven't seen before because you haven't had to test something with memory yet. Okay, but for lab 5, there's additional code that you have to put into your sim file in order to test a sequential circuit like a flip-flop or a register. Okay, and I'm giving you that code. At least this is one way to do it. There's different ways to do it, but this is a common one. See, in your sim file, between the line where you have the UUT, okay, so that between that line and where the test cases begin, you insert this code, and what this code is going to do is generate a clock for your simulation, and it will show that clock signal on your timing diagram. So it's in an always block, okay, just a straight always block. So always means that this is always running, okay? And you can see before the beginning and end, first you're setting clock to 1. And what does the number sign with the number following it?
It's 5 milliseconds. It's time. It's waiting.
Yeah, it is time. It's not.
Is it nanosecond?
It's nanoseconds.
Okay.
Yeah, because in your test cases, you see the number sign 10, like at the beginning of each test case. That's 10 nanoseconds, and we're separating each test case by 10 nanoseconds. Okay. So here, you're going to keep the clock high for 5 nanoseconds. See, this is a clock signal that this code is generating. So it's going to keep the clock high for 5 nanoseconds. Then it makes the clock low for 5 nanoseconds. And since it's always, it just keeps running. So it just keeps going. So what's the period of something that's 5 nanoseconds half the time and 5 nanoseconds the other half of the time? Yeah, this is the period, right? You all learned that in physics. Right? So 10 nanoseconds is the period of that clock. How would you figure frequency from period?
Inverse.
Right, that's inverse, right? Frequency is 1 over period. So if you took 1 over 10 nanoseconds and what's 10 nanoseconds? What's the power?
-9.
-9. You know what you would get if you reciprocate that?
100 a second.
Megahertz.
Megahertz.
Seconds here. You know why we picked this? Because your basis boards, that's what they run at. Okay, so the basis 3 boards, they run at 100 megahertz. Okay, so you see, that's why we make in between, the time in between each test case, 10 nanoseconds. That's 1 period of the frequency that the basis board is running. So basically, you're doing the test case every clock cycle. Okay. All right, so you'll know if this code is working when you look at your timing diagram of your simulation. You should see CLK, and you should see a square wave that's doing this. Okay, if your clock is not working in the simulation, nothing else is going to work. So if everything's dead, it's probably something to do with generating the clock in the sim file. Okay. All right, so the next thing is you can go ahead and copy and paste the code from this text file. Okay, this text file is on Canvas. It's under lab resources, I think, and it's it's labeled universe underscore sseg. Now, be careful because in the past, well, first of all, let me just say that we have used this module for I don't know how long, but it's been a long time. It's been at least 5, 6, 7 years, probably 10 or so years. Okay, so we know this works. Okay, so if after you copy and paste this thing, if you're getting red lines, it usually means one of 2 things. Either somehow the code got wrapped around, and you know how in System Verilog and also Verilog that the double backslashes, that's when a comment is coming. Well, what has happened in the past, and I don't know exactly why it occurs, and it's just because people aren't real careful when they do the copy paste. Well, like half the comment will be on like the following line, and it doesn't have the 2 dashes. So now Vivado thinks that's code when it's not, and that generates all kinds of errors and red lines and stuff like that. Okay, so be aware of the wraparound. Okay, after you do the copy paste. I mean, if you do after you do the paste, if you don't see any red lines, it's probably good. Okay, but another thing that you got to watch out for is, as I said before, this code is in Verilog, not System Verilog. Okay, and there's like a half a dozen differences between the 2, and sometimes it's somewhat subtle. Like for example, in Verilog they don't use logic, they use reg, and they use wire. Okay, so where we have logic for internal signals, Verilog uses the word wire instead of logic. And then how we put logic if you have an output within an always block? Well, in Verilog, they put reg, R-E-G, instead of logic. Okay, that's one of the big differences. There's other differences in how you structure, like for example, in Verilog, they don't have always FF and always comb. It's just always. And the way it's distinguished is by the equality signal or the less than or equality signal that we use within those, right? Because if it's always home, remember how we talked about using the equal sign to assign outputs, but if it's an always FF, use the less than equal like this. Well, in Verilog, you just put always, and then if you get these signs wrong, it's much more of a drastic mistake than it is in System Verilog. I mean, you still have to have it in System Verilog too, but anyway, those are some of the differences. So what has happened in the past is before a person pastes the code into the file they created, well, they create a System Verilog file, and then they put this Verilog code into a System Verilog file, and Vivado doesn't like that. Okay, so when you go to make the file, make sure you choose Verilog instead of System Verilog. you know, because you've been using System Verilog, you know, up to this point, but this is the only time you use Verilog. Okay? Okay, so once you have all that, now you can create your structural model. So now you got to put this all together. You can, I would recommend you can copy and paste what you have for lab 4, because a lot of what you need for lab 5 is also lab 4, and then you can just edit, you know, you'll have to delete anything that's connecting to this decoder and this mux. And then of course you got to add in all these connections for the memory and Dr. Mealy's time multiplexer. Okay, so and then the test cases for the overall circuit, those are on Canvas. And those test cases are the same test cases as lab 4, but you also have to show that reset works, you know, clear works, and also you have to show that the memory is working. Okay, because now that we've added memory, the result that you see on the 7-segment display, it shouldn't change until you hit the enter button. Okay, so, you know, say there's a result being shown on your 7-segment display, and now you go to change the switches for the next addition or subtraction. Well, as you're changing the switches, right, on the input, that display should just remain showing the old result. It shouldn't update to the new addition or subtraction until you hit a button, right, the enter button. Okay, so you'll know if your memory is working, because if the display is changing as you're changing your switches, that means your memory's not working. Okay, and then also you'll know if your reset's working, because you just hit a button, you know, your reset button, and the display should go from whatever the previous result was to 0, right? When we reset, it makes all the outputs of the Q, the register or the flip-flop equals 0. Okay. Let's see, what else did I want to talk about here? Oh, very important. And this is one of the reasons why, you know, I had you watch that video last week, the Dr. Benson video, the troubleshooting video, where you can pull out intermediate signals and put them on your timing diagram. And the main reason for that technique is when you have to troubleshoot, right? Because it allows you to trace the signal through from input to output when you have a problem. But for this lab, there's another reason why you need that technique. And that's because of the time multiplexing, the timing diagram for the seg output and the AN output of the time multiplexer, when you look at it on the timing diagram, it's not going to make any sense. Okay, because the simulation can't show you how the time multiplexer is doing its thing. Okay, it's just not a capability of the simulator. So the way that you test that lab 5, the overall circuit is working, is that you have to look at what's going into Dr. Mealy's module. See, we know Dr. Mealy's module is good. Like I said, we've used it for like 10 years, so we know it's good. So if what's going into his module is good, you can bet on that it's going to work on your board. Okay, so what that means is you have to pull out the signal going to input CNT1. Okay, and you have to pull out the input going to the sign input of Dr. Mealy's module. And also you got to pull out the valid input of Dr. Mealy's module. Okay, so, you know, write that down or make a note, because I can't tell you how many times I'll get an email from somebody and they're like, Gary, I've been working on lab 5 the last 3 hours and all my lower modules are working, all my connections are good. But I look at the output of, you know, the seg and AN on my timing diagram for the overall, and it doesn't make any sense. And I just emailed back, it's not supposed to make any sense. You know, so you've got to look at what's going in. Now, let's see what should be going in. Look at the CNT1 input of Dr. Mealy's module. Look what it goes to. What is it going to? It's going to the top register, and how many bits is that register? 4 bits. And then look at the D input of that 4-bit register. Where is it going to? T5, which is what? It's the D input of that 4-bit register, but where is it going over in your lab 4 design? Like where is yeah, it's going to what used to go into your decoder, right? Well, what was going into your decoder? Yeah, that's the result, right? So you see that 4-bit register at the top, that's storing the result of the addition or the subtraction. Okay, and that's what's going to Mealy's module, is what's coming out of that register, right? Okay, how about the middle? Now it's called a register, but how many bits is that middle module there? It's just a single bit. See, I mean, really, that's just a flip-flop, right? Because that's what a flip-flop does. It stores a single bit. I mean, it's kind of, it's not exact to call a flip-flop a register, right? Because like we said before, register stores multiple bits, right? This module, in fact, the bottom 2 modules are just storing single bits. So they're really just flip-flops. I guess it's not incorrect to say it's a 1-bit register. Okay, but really it's just a flip-flop, right? So see the middle module and the bottom module of our memory, those are just flip-flops, right? That's going to be what you model and test here, right? It's just the top one that's 4 bits, that's a register. Okay, so what is the purpose of the middle 1-bit register or flip-flop, whatever you want to call it? I mean, the purpose of the 4-bit is to store the number, right? The result. What's the purpose of that middle register? What's it storing? Yeah, the sign bit. See how the output goes to input sign of Mealy's time multiplexer? How about the bottom flip-flop? Yeah, it's storing the valid bit. All right, so you see, if you trace back the D input of the middle one, T6, lo and behold, it's going to the output of that AND gate that was determining whether we had a negative or a positive result, right? And in lab 4, we were using an LED to show whether it was negative or not. In lab 5, Mealy's module, when that sign input is a 1, meaning it's negative, it's going to show a dash on the furthest to the left 7-segment display. Okay, so instead of an LED showing it's negative, now we're using a 7-segment to show it. Okay, and then the valid, in lab 4, we're using that mux that would make it blank, right? All the displays blank if it was invalid. Well, Dr. Mealy's module, if the valid input is a 0, meaning it's not valid, all the displays are going to show a dash. Okay. Now, here's the last thing. Let's see. I think I covered it all, but well, this was this over here. The inputs. Yeah, kind of got ahead of myself. Let's see. Let's make sure we didn't miss anything. So we talked about all this, right? Talked about that. We'll get back to this. Yeah, key input. We talked about this. We're going to talk about that. Let's see. We talked about this, right? You got to delete the decoder, delete the mux validity, add 2 D flip-flops, add 1 4-bit register, right? We talked about what the register is storing, right? That's the binary number of the result. We talked about what the middle one, right? That's the sign bit, the bottom one, validity. Okay, so we just got a few more things here and then we're done. First, remember we talked about bit mismatch? We talked about that, right? It was a while ago, but we talked about it. There was an activity where in the activity it showed how concatenation can be used to solve bit mismatch. You might have to go back and look at that activity, although you probably studied that for the exam, so maybe it is fresh in your mind. Well, look, we have a bus mismatch where the Q output of the 4-bit register connects to the CNT1 input of Dr. Mealy's time multiplexer. See, Dr. Mealy designed his multiplexer to take in a 14-bit number, but we're only dealing with 4 bits. So if you were to directly connect 4 bits to 14 bits through an internal signal T8, you would get a bit mismatch. Now, depending on which version of Avado you have, like I think the newer versions will take care of bit mismatches themselves, like you don't have to do it. The older ones, it won't take care of it. It either gives you a critical warning or an error. It won't like it if it's an old. But you should know how to fix it. I mean, how would you fix that? How would you fix that bit mismatch where you got 4 bits here at this Q output, but you got 14 bits for the input to the time multiplexer? Yeah, how many? And where will you add them? To the left of that number or the right? Yeah, left, because you don't want to add it to the right. That would change the value. Okay, so yeah, you should be able to solve that. Okay, so that's a little, little review. All right, next thing, because if I don't bring this up, people think it's a mistake. And that's, okay, take a look at our clear input. Here's our main clear input, right here. And it connects to the clear of the 4-bit register that's holding the number, right, the result. It goes to the clear of the sign bit. But then look, the clear, the main clear, it doesn't connect to the clear of the validity flip-flop. It connects to the set. And that's not a mistake. See, sometimes people think that's a typo. They end up connecting it to the clear, like the yellow tree, but it's not supposed to. It's supposed to connect to the set. Does anyone know why it goes to set instead of clear? This bottom flip-flop that has to do with validity, while it goes to clear for the number and also for the sign.
Says valid. This valid is one. Valid.
Right. Because what would happen if instead of connecting to the set, we connect it to the clear for validity? Well, close.
That's assume it's unvalid.
Right, and the way Mealy's module works is that if it's invalid, it's going to show dashes. But if we're clearing something, what do we want it to show? We want it to show 0. So by clearing the top register, that's going to make the result 0. And by clearing the sign bit, that's going to make it show no dash instead of a dash. And by setting the validity at the same time we're clearing the others, that will put a valid on the input of Mealy's time multiplexer, which will show the 0, right? Because if we didn't set it, instead of showing zeros when it was cleared, it would show dashes because it would take it as invalid, right? We want the reset to be valid, right? So it shows the zeros. Okay, so that's another thing you might want to make a little note of, because I can't tell you how many times I get an email and someone goes, everything's working, but when I go to reset it, it shows dashes. All right, if I had a nickel every time I got an email like that, I'd be a rich person. Okay, so that's a very common, it's understandable. I mean, it's an understandable mistake, but it's still a mistake. Okay, and anywhere you see the ground symbol, what are you going to connect those inputs to? 0. Okay. You've seen that in other, have we seen that? We've seen it with a 1, right? You connect it to a 1. Ground, for those of you that haven't had circuits, ground represents 0 volts, or we call it 0 volts. Okay, so anywhere you see a ground symbol, just you connect it to 0. Okay. All right, I think this is the last thing, and unless you have questions. And that's in the constraints for lab 5. The seg portion and the AN portion, you have to do the numbering reverse of what you did in lab 4. Okay, in lab 4, you numbered from top to bottom, like 0 through 7 for seg and 0 through 3 for AN. The way Dr. Mealy designed his time multiplexer, you have to number them the other way. Okay, so for AN, instead of going 0 to 3 descending, you go 0 to 3 ascending. And instead of going 0 to 7, where you don't put anything for the decimal point like you did for lab 4, in lab 5, you start with the decimal point, that's your 0, and then you go ascending to 7. Okay, so you can just copy and paste or cut or bring over your constraints file for lab 4 and then just edit the numbers the other way. Okay. If you don't do that, if you do the same ordering as lab 4, you're going to get gibberish. it's gonna look all kind of, just, you know, because all the segments are, you know, not making any sense. Okay, all right, so I think that's all. Any questions? Let's see that, I didn't miss anything over here. Do you have any questions? Because now what you can do, and there's no activity today. But what you can do is, you know, work on lab 4 first, right? That's your next priority because that's due on Friday. And then, you know, anyone that's done with lab 4, I mean, did anyone finish lab 4? I think, oh, okay, great. Yeah, there was one other student that finished. I was amazed. She stayed a couple of hours and she finished during one of my other sections. So yeah, if you're done with lab 4, you're way ahead of the game. So, you know, if you want to start into lab 5, of course, you can, but like I said, that's not due for another week and a half or so. Okay, so any questions? If not, we're done for the day, and I totally understand if you want to go chill someplace, you have an exam, you know, if you want to just go relax. You know, you got time to do the assignments, but don't put off lab 4 too long.
Yeah, I don't.
Oh, that's okay. You can take a picture.
That's more than fair. It's